Hello, and welcome to G Fun Facts Online, your go-to source for fascinating insights into the world around us, and sometimes worlds beyond our everyday experience. Today, we're diving deep into a topic that sounds super complex, but is incredibly cool and fundamental to how we understand the universe at its most basic level: operator algebras. Now, I know what you might be thinking. Operator algebras sounds like a math headache. But stick with me, because this is a story of how a seemingly abstract mathematical idea, born from the mind of the brilliant John von Neumann, became the backbone for understanding the weird and wonderful world of quantum mechanics. Imagine needing a whole new language to describe how tiny particles behave. Well, von Neumann essentially helped create it. So, what are these operator algebras? In simple terms, they are a branch of mathematics that studies special kinds of mathematical structures, specifically algebras of what are called bounded linear operators on Hilbert spaces. Think of them as sophisticated toolkits that mathematicians and physicists use to handle the bizarre rules of quantum systems. The two main stars of this show are C** algebras, pronounced C-star algebras, and von Neumann algebras. These aren't just dusty old concepts. They are vital. They provide the natural language for describing observables, things we can measure, like energy or position, and states in quantum systems. And this connection has only gotten deeper, especially with the explosion of quantum information science. You've probably heard buzzwords like entanglement, quantum channels, and quantum entropy. Guess what? These concepts are deeply intertwined with operator algebras. It's like discovering that two different fields of science were speaking dialects of the same language all along. One of the most exciting proofs of this synergy was the recent resolution of the cone embedding problem. This was a massive, long-standing question in operator algebras that had stumped mathematicians for decades. And how was it solved? Using cutting-edge techniques from quantum information theory and quantum complexity. How amazing is that? It's like a detective story where the crucial clue comes from an unexpected witness. This breakthrough has flung open doors to entirely new research avenues, bridging these worlds even further. Let's delve into some key theoretical aspects, because this is where it gets even more fascinating. There's a huge ongoing project to classify C** algebras. Think of it like how biologists classify species. Scientists are trying to create a systematic understanding of these complex mathematical objects. It's a massive challenge, but progress is being made, sometimes using methods from entirely different mathematical fields like order theory. Then there are von Neumann algebras. These are absolute superstars in what's called algebraic quantum field theory, where they model local observables. But it gets cooler. Recent research shows they're crucial for understanding entanglement entropy in quantum field theory and even in quantum gravity. Yes, we're talking about black holes. Type 2 von Neumann algebras naturally pop up when describing what you can observe around these cosmic behemoths. Mind-bending, right? And the party doesn't stop there. Ever heard of quantum groups? They are like the quantum cousins of the symmetry groups you might have learned about in geometry, and they're vital for understanding quantum integrable systems. They also have profound connections with operator algebras. This leads us to non-commutative geometry, pioneered by the legendary Alain Kohn. This field uses operator algebras to extend geometric ideas to spaces where the usual rules of geometry don't apply. Spaces where, for instance, x times y doesn't equal y times x. And this isn't just abstract fancy. It has applications in areas like the Standard Model of particle physics. Another gem is subfactor theory. This theory, which grew out of the work of von Jones, studies special ways von Neumann algebras can be included within each other. It sounds niche, but its impact is massive, reaching into mathematical physics, low-dimensional topology. Ever heard of the Jones polynomial for classifying knots? That's from here. And even the study of two-dimensional conformal field theories, which are super important in understanding certain physical phenomena. It also connects to quantum statistical mechanics and exciting new states of matter called topological phases. Now let's talk about emerging applications, because this is where the theoretical rubber meets the real-world road, or perhaps the quantum highway. In quantum information theory, operator algebras are indispensable. They help analyze quantum correlations, like spooky entanglement, determine how much information can be sent through quantum channels, figure out strategies in quantum games, and even underpin concepts in zero-error quantum information. Essentially, they're helping us understand the ultimate limits of information processing and develop new quantum algorithms and super secure cryptographic protocols. There's even cool research on quantum graphs, which pop up in quantum channel theory. Then there's quantum computing. The very framework of operator algebras supports many aspects of building these futuristic machines. For example, research into quantum error correction, which is crucial if we want stable quantum computers, benefits hugely from insights from operator algebras. Developing quantum algorithms to solve complex equations or simulate quantum systems also leans heavily on these mathematical tools. Operator algebras also have a long and fruitful relationship with quantum statistical mechanics. They provide the tools to describe systems in equilibrium using something called KMS states, and more recently, they're helping us tackle non-equilibrium phenomena in quantum systems, things like understanding entropy production in systems that are constantly changing. And let's not forget condensed matter physics. Here, especially through subfactor theory and conformal field theories, operator algebras are contributing to our understanding of topological phases of matter. These are exotic states of matter with weird properties that could lead to revolutionary technologies, and they're a major focus in physics today. So what's next for operator algebras? The future is incredibly bright. This interplay between operator algebras and quantum mathematics is a hotbed of discovery. Researchers are working hard to solve more big open problems, like the hyperlinearity conjecture, using these powerful quantum information approaches. The dream is to develop even more powerful mathematical tools for theoretical physics and to explore even deeper connections between operator algebras, quantum computing, and quantum gravity. The ongoing efforts to classify C** algebras and the application of these algebraic techniques to understand complex quantum weirdness promise many more breakthroughs. There are workshops and conferences happening all the time, bringing brilliant minds together to push the boundaries of our knowledge. So, from the quantum realm to the fabric of space-time, operator algebras born from a need to understand the very small are now helping us unlock secrets of the very large, the very complex, and the very, very weird. It's a beautiful testament to how abstract mathematical ideas can have profound and far-reaching impacts on our understanding of the universe. That's all the fun facts we have for today on G Fun Facts Online. I hope this peek into the world of operator algebras has sparked your curiosity. Join us next time for more amazing discoveries. Thanks for listening.